All right, good morning. This is section 9.2, tests about a population proportion. So I did record today's class, but I didn't really like the way it was recorded, so I'm going to redo it. And this will be today's recording. And why is this here? I don't know why that's there. There we go. Okay, so tests about a population proportion. We talked about this last week. Today we're going to get into more of the specifics about how this is done. These are the learning objectives. Feel free to pause here and read through these in a little bit more detail. We're going to work through them. So here's an example. So let me get rid of that. Okay. So suppose a researcher is conducting a study of charitable donations by surveying a simple random sample of households in a certain city. The researcher wants to determine whether there is convincing statistical evidence that more than 50% of households in the city gave a charitable donation in the past year. Let P represent the proportion of all households in the city that actually gave a charitable donation in the past year. Which of the following are the appropriate hypotheses for the researcher? So last week we talked about this, and hopefully you remember that HO always has to have an equal sign, so we can cross out this one and this one. So HOP equals 0.5. This is, we're hypothesizing that the true proportion is equal to 0.5. The alternative is that the person thinks that maybe there are more than 50%, so P is greater than 0.5. All right, so hopefully you remember that. Okay, the null hypothesis. We are assuming some value for P. Let's call it P with a little zero, P0. It's a hypothesized value. The alternative, assume that P0 is not the true value of P. Instead, we assume it's either less than, greater than, or not equal to. Okay, there are so many P's, so let's just review them. The probability of something, we have P of something is probability. Lowercase p is used for a population proportion. P with a hat is the sample proportion, and P0 is the assumed value of a population proportion in a hypothesis test. All right, when we carry out a significance test, also known as a hypothesis test, we have to check the conditions. The conditions are the same as they were previously for Chapter 8 for confidence intervals. So what are they? Let's just quickly review. Random, your sample must come from a random sample. NP and NQ, I'm going to start using Q now. Q equals 1 minus P, just in case you forgot that. Let's write that down. Q equals 1 minus P. So P and 1 minus P. NP and 1 minus P or NQ has to be greater than or equal to 10. All right, and that's so that we can use our normal calculations. And the third is that we can't sample more than 10% of our population. So that's what that means. Small n is the sample size, capital N is the population. So here we have our basketball player again. I'm really tired of him, but here he is making his free throws. He claims he's an 80% free throw shooter, but in a sample he only made 32, which is 64%, which is a lot lower than 80%. Is this convincing evidence against his claim? So you might say yes, but what we're going to do is we're going to run the test just to be sure. So first we set up our hypotheses. And so HO, there is a tiny little colon here, you probably can't see it. HO colon, P equals 0.8, and we think actually P is less than 0.8, so that's our alternative, where P is the actual proportion of free throws the shooter would make in the long run. Okay, so when the conditions are met, here they are again, then the sampling distribution of P hat is approximately normal with a mean of P, which is the actual population proportion, and a standard deviation of the square root of P1 minus P over N. When we did confidence intervals, we didn't know P, so we used P hat because that was the best we could do to obtain the standard error. For hypothesis tests, the null hypothesis specifies a value for P, so we're going to use that value. So this is one of the significant differences between doing a confidence interval and a hypothesis test. So here's how we come up with our standard deviation. We have the 0.8, which is the hypothesis value, times 0.2, 1 minus 0.8 over 50 gives us this for our standard deviation. So if we assume that HO is true, then the P, which is the mean of our normal distribution, is 0.8. So here you see 0.8. Let me move this down just a little bit so you can see it. Oops, move it up a little bit so you can see it a little better. Okay. Actually, move it up even more. So we have our normal distribution. The mean is 0.8, which is our hypothesized value. The standard deviation is 0.0566. So the value that we got, or that he got when he shot 32 out of 50 shots, 0.64, is way over here. So we can see that, this right here is pretty small, and therefore the assumption that he did this just by chance, that he actually is an 80% free throw shooter, but just by chance he only made 32 out of 50. The probability of that happening, we haven't calculated yet, but we can see by looking at our normal distribution that it's pretty small. It's just a very small piece. Okay. So how do we carry this out? We're going to turn these numbers into a z value using our formula for z. Remember, z equals x minus mu, that x value minus the mean over sigma. So in this case, we're using the test statistic is z. And the reason they don't call it z is because later on, when we talk about means, we're going to have t instead of z. For now, we have z is equal to the test statistic, which is our 0.64, minus the hypothesized parameter 0.8 divided by our standard deviation is negative 2.83. So what does that mean? It means if we go back to our normal curve, the probability of this happening, this is z, is negative 2.83, is 2.83 standard deviations below the mean. Okay, now we can calculate the probability by using normal CDF, which I don't know if we actually do on the next slide. Oh yeah, we do. Okay, so the probability using normal CDF gives us what's called the p-value. So normal CDF, try to write this, normal CDF, sorry, I'm writing with my mouse, CDF, lower, negative infinity, negative 1,000, upper is going to be our 0.64, our mean is 0.8, and our standard deviation is 0.0566. Put that in. That's going to give us a probability, which is our p-value, 0.0023. Okay? As an alternative, you can also use the z-score and do normal CDF using the z-score. So that would be normal CDF, negative 1,000, and instead of using 0.64, we're going to use negative 2.83, 0, and 1 as our mean and standard deviation. We get the same p-value of 0.0023. The shaded area under the curve gives us the p-value and the z-test statistic. There are two options for calculating the p-value. The first is what we just did, find the z and then use normal CDF. Or, much simpler, but also less popular on the AP test, to use on the calculator one prop z-test. So what does that look like? I'm going to pull up my calculator here so you can see. So here's my calculator. Move it over so you can see it. So we do stat, tests, and one prop z-test is number 5. So I'm just going to hit 5. And I've already got the data in here. As you can see, p0 equals 0.8. X is 32. That's how many shots he made out of 50 shots. And we think it's less than 0.8, so we say less than p0. And then we go down and we calculate. And I'm actually going to, I could calculate or draw. If I select draw, then it's going to draw me a normal curve with a picture. Notice there's really no shading here. If you look really closely, it might be just a tiny bit because it's so far to the left. It's almost 3 standard deviations to the left, so it's right about there. Z is negative 2.8284, and P is 0.0023. We're interested in both of these numbers. This tells us how many standard deviations we are away from the mean, and this tells us the probability of getting these results, assuming that HO is true. Okay, so here, let's see. Well, this is just more about how to do it on the calculator. We're interested in the p-value. Well, let me go back. Okay, so 0.0023, I think it was, is very, very small. This is the probability of getting these results out of an 80% free throw shooter. Since this is, let's say alpha is not provided, but usually we just set it at 0.05. This is way less than 0.05. We make the conclusion that we reject HO. Okay, I should type this, it'd be easier. Reject HO. In favor of the alternative, we do have evidence to say that our free throw shooter is not an 80% free throw shooter. Okay, when you're doing these, this is the 4 steps that you should follow when you're doing an open-ended question on the AP test. So I'm going to give an example of what this looks like in a lot of detail. But first, what hypotheses do you want to test and at what significance level? So we would say in the example we just did, we want to test the hypotheses HO, P equals 0.8, and the alternative P is less than 0.8, where P is the true proportion of shots that our free throw shooter would make over a long amount of time, many, many shots. And the significance level wasn't stated, so we're going to say let alpha be equal to 0.05. Okay, we did define the parameters P is equal to the proportion. All right, choose the appropriate inference method. One sample z-test for proportions is the full name. One sample z-test for a proportion right up here. One prop z-test is the short way to say that. Check your conditions. So in this case, we would check random, assuming shots are independent and random of each other. In this case, there is no specific number of shots. He could just keep shooting forever, so that doesn't apply, the 10% rule. And if he shoots 50 times, n is 50 times 0.8 would be equal to 40. We would expect 40 and then 10. So we'd expect him to make 40 shots and miss 10. So both of those are greater than or equal to 10. So we are okay. If the conditions are met, perform the calculations. We did that, the z-statistic, the p-value. If you're using the calculator, you can just say, I'm using on the calculator one prop z-test, define what you put in, and then make sure to list this and this. Okay? Make a decision about the hypotheses in the context of the problem. So make a full statement that says we either reject or fail to reject the null hypothesis that the shooter is not an 80% free throw shooter, that he shoots less than 80% because our p-value of 0.0023 is less than our significance level of 0.05. Okay, this kind of says the same thing we just went through. So you can take a second and read that. The p-values come from the standard normal distribution. All right, so now when you do these tests, here's the formula for z. This is what we did. So it's p hat minus p0 over the standard deviation, which is p0, 1 minus p0 over n. Okay, you can have a one-tailed test, which is, and this one is a right-tailed test, because here we're assuming that p is greater than p0. A left-tailed test where we assume p is less than p0. Or you can have a two-tailed test where we assume that p is not equal to 0.0. So we want to find the probability of getting the results that we got in either direction. So we're going to do an example of that next. Okay, where p0 is the assumed value of p in the null hypothesis. Why would we calculate z when we could just use normal CDF? Including the test statistic z shows better communication and is the long-established standard of statistical reporting. Rubrics typically require a test statistic in addition to the p-value. So it's a good idea to calculate z and show that you really know what you're doing, but in the absence of time, if you're really short on time, you can use the one prop z test. Just make sure that you write down z. Say what z is and say what p is. Okay, and then use one prop z test to check your work. If you have time, enter all the values, calculate. All right, two-sided tests. In a two-sided test, the alternative hypothesis has the form p is not equal to p0. The p-value is the probability of